As chief architect for system software and the father of OS/2, the insights that guided Gordon Letwin in the design of OS/2 are of more than passing interest to us all. In this next talk, Gordon will be sharing these insights with us, along with their implications and some of the alternatives that were considered as OS/2 evolved into its final form.
My name is Gordon Letwin. I'm giving a talk called OS/2 Design Concepts. This is a talk that's a general overview. We don't get into a lot of technical details. It's a talk that I thought was important to give because all the data you've received in this package and these other talks open bottom-up data. You're sort of drowned in a variety of detailed features and detailed pieces of data, and there's not a whole lot of information you get as to how all this fits in, what the overview of the structure is here. It's hard to see the underlying pattern because of all the data being given, so I'll try to address that some in this talk. One of the reasons it's especially hard to see the underlying pattern of the operating system is because there's so many different ways to do things. This is definitely not a minimal system. There's a couple of reasons why there are so many different ways to do things in this operating system. One of the reasons is because we have to be all things to all people. It is a protect mode operating system. If the operating system doesn't do it, then it can't be done. In a traditional environment, operating systems were sold into mini computers and full-size computers working in a technical environment. And there's usually some local hacker there who can customize the system. That's not the case in this environment. There isn't a local hacker, sources aren't available. Your applications have to run in the field on standard systems. So if the feature isn't in the system, then it doesn't exist. That tends to bring in extra features. The system is not really a random hodgepodge, as you might get the impression just looking through the manual. It's actually a controlled hodgepodge. To give you an example of what I mean, in the field of inter-process communication, we have architectural precepts, we have what we call architectural religion, we have guidelines and goals. We basically produce a list of wills and won'ts for the inter-process communication mechanism, what it's supposed to do and what it's not supposed to do and how it's supposed to accomplish its goals. Once we have that architecture, that framework set, then we may have 3 good forms of IPC, and if there's a reasonable argument for a fourth form of inter-process communication, then we'll stick that in too. If some important people insist there's got to be a 5th form and we can't come up with another way of providing that functionality, then it's conceivable we can get a 5th form too. It costs us some manual pages, it costs us a few more bytes of code. Many of those bytes can be swappable if the code's not being used and they aren't too painful. The key thing is that there is an underlying architecture. Things aren't randomly put into the system. Within that underlying architecture, there are a lot of times can be a variety of different ways to do something. Another key topic I'll get into is contrasting operating system 2 with standard mini-computer operating systems. Standard mini-computer operating systems were multi-user systems generally. Their goal was to maximize throughput and maximize machine utilization. Machines are very, very expensive. People weren't so expensive. If you had a dozen people on this machine, the idea was to maximize the throughput. Maybe we could put a 13th person on the machine. That would be worth a lot to us. We also tried to maximize fairness in a mini-computer environment. If you've got 12 users, you want to be fair among those. You don't want one user, because of some characteristic, to get half the CPU time. Consequently, the mini-computer environments generally ran in a pretty frugal environment. They a lot of times worked over glass TTY, sometimes 300 baud. Unix, for example, is famous for its short encrypted commands, but Unix was used very, very heavily by people dialing up at 300 baud. And at 300 baud, the shorter the commands are, the better. The operating system 2 environment is quite a bit different. It's a microcomputer operating system. It's aimed at single-user systems, and its function is to maximize the utility of the system to the user. We want to maximize the utility of the system. We want to maximize the response. We're willing to spend CPU resources, and we're willing to spend memory resources to make the system more usable, faster, and more responsive. We're worried a lot less about throughput, and there isn't any fairness issue. There's only the single user. When I list the major features, I'll compare and contrast sometimes the mini-computer environment to the OS/2 environment and how they differ. Some of the major features of OS/2 that I'll talk about from a global perspective. Graphics is very, very important to us. When we started the system, we knew that graphics and these other features on the slide were a requirement for this operating system. Graphics specifically is what we call the GUI, GUI, for graphical user interface. The human eye is a very high bandwidth device. It seeks very, very rapidly. You can move your eye around very rapidly. We have special hardware built into our brains for recognizing patterns and for picking up data visually. Recognizing patterns and exceptions to patterns was very, very important back when that pattern or that exception to pattern might be either your dinner or it might be someone who wants you for your dinner. We have a lot of capability in us to that deal with visual data, very, very complex visual data. To take advantage of that visual data, it makes sense to have a system that provides a graphical interface. If you look at the capabilities of the Xerox Star system, the Apple Macintosh system, and various graphical systems of that nature, the Microsoft Windows system, obviously, you can see that those systems provide a great deal of more benefit than character-oriented systems do. Even within the realm of character-oriented systems, many of you are probably familiar with line-oriented editors, such as the infamous Edlin. If you play with a line-oriented editor, then later on you change to a screen-oriented editor, there's just no question that the screen-oriented editor is very, very much more powerful, even though it deals with a whole bunch more CPU resource and burns up a lot more effort writing a lot more characters to the screen. But it's greatly worth it to the user. So long as you can afford a computer that can support a screen-oriented editor, you want one. The same is true about a high-resolution graphical environment. So long as you can afford a computer like that, you want one. And affording is comparatively easy to do nowadays. If you were to take a time machine and go forward in time and look at what the office automation home computer environment would look like, there's just no question that if you run your time machine far enough forward, that high-resolution graphics would be the way to go. The benefit of those can be shown to be very, very high today, and as people get smarter about using it, they'll become higher. The cost is pretty low today and will become arbitrarily closer. Those two lines do cross sometime in the future. There's room for argument about exactly what that interface will look like. There's room for argument about what the interface should look like. But the fact that high-resolution graphics is what the future holds, there's just no question about that. The only questions might be what it would look like and when it would take place. I believe it will take place relatively rapidly, and it will look a lot like the presentation manager in OS2. But irregardless, graphics was a key issue for OS2 to support. Minis typically don't address high-resolution graphics very well. It takes a lot of RAM to map that screen image. It takes a lot of CPU horsepower to flip all those RAM bits. And then once you've done that, you have to do it for all 16 of your users. It's very, very difficult to achieve. Things like 3270s, for example, which are generally character-oriented, they even offloaded some of that processing down to the terminal itself to try to relieve the burden on the CPU. Minis, for that reason, didn't do very much good support of high-resolution graphics. This microcomputer environment would do a much better job. Multitasking is another key requirement for the environment. Multitasking is traditional in minicomputer operating systems, and there's not a whole lot of difference except the scheduler. As you mentioned earlier, minis optimize throughput, whereas OS2 optimizes response. Memory management is also a key traditional characteristic of minicomputer operating systems. The major difference here is the swapping algorithm. Minicomputer operating systems are always trying to put 10 pounds of data in a 5-pound bag. Memory was super, super expensive, and the fact that you could slow down your response by 30% but maybe fit a few more programs into memory or avoid having to buy an extra 128 gigabytes of memory, that was worth a great deal of money in the minicomputer days. It's not worth a great deal of money today, and it doesn't make sense to basically run too many programs in a system and slow down the response by swapping it when all those programs come from a single user. So one of the advantages that an OS2 environment allows us to do is if the system thrashes too heavily, the user can be explained, can be told what the situation is, and the user can either run fewer programs, buy more memory, or be patient. It's possible that this is a one-time event. He'll just go out for some coffee. Protection is a key issue. Current machines don't have any good protection in them whatsoever, and the issue hardly ever comes up. Current machines are like sophisticated desk calculators. They sit on your desk and they work with data that you bring to them. They're secured by basically the same mechanisms that secure your desk calculator and everything else, the traditional mechanisms. You have a lock on your office door, perhaps. You have a lock on the front of your building, perhaps. You may have security people in the hallways. If somebody's sitting at your desk, seen playing with your stuff, then that looks pretty suspicious. In a network environment, though, that will change quite a bit. We've heard talks about the future of the office automation environment and the networking environment. When you get to the point where a mailroom clerk can peruse all the personnel files, he can peruse the payroll files, he can give himself raises, he can see secret marketing plans, he can find out who's carrying on with who in the office corridors, that's going to be disastrous. And he doesn't take a mailroom clerk who's a super programmer. All it takes is a mailroom clerk who knows to order some program out of the back of some computer magazine, the equivalent of the copy protect violation programs that are for sale today. Those programs will exist if holes exist in the security of the system. And a system that has those kind of holes in it will just not sell very well and will not be acceptable in the office of the future environment, the heavily networked environment. It's my guess that you won't see much about this until someday there will be some major publicized disaster, and then all of a sudden people will then realize this is an issue. OS2 has been designed to be so that it can be made fully secure. OS2 is not secure in the 286 environment for two reasons. Number one, so long as you run a real mode box, we're running in true real mode. An application running in that box can do anything he wants to anything, and we can't stop him. So the real mode box is an incurable security hole. The other aspect is the fact that there are currently no file system protections, so we can't prevent a Trojan program, basically a malicious program, from modifying files arbitrarily. OS2 is designed so that those loopholes can be closed. In the 386 environment or the 286 environment, whether you're not running the real mode box, we can close those loopholes out completely. In the 386 environment, even with the real mode box, with multiple real mode boxes, there are no security-related issues whatsoever. Also, in the future, protected file systems will be available with permissions based on their files. When you're running either on a 386 or foregoing the real mode box in a 286, and you're using the protected file system, then you can produce a system that is fully secure so long as your boot time binaries are trustworthy. The kernel itself has to be trustworthy. If somebody can convince you to run a special patched version of the operating system, then obviously there's no security can be held. The device drivers that you bring in, the things listed in your config.sys file, those all have to be trusted. Once those are trusted in a secure environment, OS2 is designed so that nothing else, no Trojan program, can violate system security. Interprocess communication and basically the tasking architecture was a critical design characteristic. We didn't want to force applications to do everything for themselves. Today, an application running in a DOS2, DOS3 environment, he either does the work himself or the work doesn't get done. There's nobody else providing these services for him. You end up with packages like Symfony and so forth that are these all-in-one packages that try to be all things for all people. Minis typically didn't have very, very good interprocess communication. Some of them weren't too bad. Some of them were kind of poor for a variety of reasons. In the micro environment, though, it's important in the design of OS2 that no application has to reinvent the wheel. Services will be available in various forms, and applications that need those services should get them. Some people might think, gee, this is kind of wasteful. Here I am, I'm writing a spreadsheet program, and why should I call up a database package to provide database services? Wouldn't it be more efficient if I did it myself? Well, it wouldn't. Look at a hardware kind of environment as an analogy. For a company that's putting together a PC clone, for example, that company will typically go buy a power supply from somebody. It comes in a little box, they just drop it right in there. Now, if you actually thought about it, that power supply has got some components inside it that may not be necessary. Maybe it's got 3 or 4 resistors to deal with a certain kind of situation, and because I'm designing my computer, I know that situation can't come true. I could tell myself, heck, if I did my own power supply, I could leave out those 4 resistors, think of all the money I'd save, but in practice, I wouldn't. I get my own power supply. It takes me longer to produce my product. It takes it longer to get to the field. I don't have the advantage of these other guys' volume production and their expertise in power supplies. In general, I end up with an inferior product by not using a standardized facility. If you use a standardized facility, you get enough gains. You get enough gains in your productivity and enough gains in performance that the fact that you may have that the standard product has a little bit more than you really need doesn't really hurt you. That same thing is true in a software environment. You want to use specialists to provide these various services, and those specialists will probably do a better job than you'd have in your code having to duplicate all the functions of those specialists. You may waste a few CPU cycles. That's not really a problem. If you really have to do it yourself, you're welcome to do it yourself, but it rarely makes sense. Where are these services coming from? They're out there in the field being developed today, and they'll be available over the next few years. Basically, the key thing for system services in the Dynalink environment is to set a standard. The services that are provided as part of OS2 have already set a standard. They're present in every OS2 system, and that standard is therefore set. So VIO, for example, the graphical presentation services, those are very, very important services. It's very difficult to write something like the presentation manager. That service is established, and that standard has been set. A database service, for example, that standard hasn't been set. Other kinds of services, the standard hasn't been set. That standard doesn't need to be set by Microsoft. That standard could be set by third-party software vendors. The operating system environment through the Dynalink mechanism is arbitrarily extensible. As an example of some of the facilities, some of the things that can become available through an IPC mechanism, and the services you can provide. Take, for example, a word processor such as Microsoft Word. We can provide a dynamic link interface to a future version of Microsoft Word that exports Word services to programs as well as to users. Well, why would a program ever want to invoke a WYSIWYG, what you see is what you get, screen editor? Well, for example, a program can invoke a Word service that says, look at this file, tell me if this is a Word internal representation file. Another service might be to translate an internal Word file into a TTY file, or to provide certain data or to extract text from that file. A great deal of services can be provided to the inter-process communication mechanism, and that's a key architectural issue of OS2. I'll talk some about some of the other design goals we had and some of the contradictions that were inherent in those design goals. For starters, we needed device-independent graphics device drivers, but we needed to do that without significant device overhead. Device independence is comparatively easy to achieve. You have a very simple virtualized device that represents a subset of what all the hardware can do, and everybody calls to that standard interface to a device driver. And that provides you device independence, and it's very, very easy to achieve. The problem is that you've used the lowest common denominator of your hardware, and also because you're funneling everything through a device driver interface, you're really taking a performance hit. I just finished going on at some length about the importance of graphical interfaces, and that will bring in things like mice, you could bring in things like light pens and digitizer tablets, a great variety of things, fax machines and so on, front-ending into these processors. So we wanted to hold device independence because of the great variety of devices that would be out there, but we needed a mechanism that provided very, very high performance. And that's the genesis of the presentation manager and the VIO interfaces. Another issue we had was direct access to high bandwidth peripherals. Even when we provide this variety of services, there may be some peripherals, and I'll mention again fax machines and so on, where an application, a specialized application whose sole job is to run this peripheral needs to have direct access to it. We wanted to allow applications to have direct access to peripherals, but we didn't want to have a Wild West free-for-all. It's important for us to know which applications are addressing which peripherals and to make sure that that's a legitimate thing to do. We don't want applications addressing the hard disk controller because that would therefore destroy any possibility of having a secure file system. We achieve that effect by means of a variety of mechanisms. As was discussed in earlier talks, if you ask the operating system for permission, if the device driver grants permission, then applications can have direct access to devices. So the basic model is every device has a device driver, and that device driver has to grant permission to individual applications to have direct access to that device. So in the case of a fax machine, for example, the device driver may be a stub driver whose sole function is to grant permission to the special application to use that device. But that gives us not only direct access, but it gives us the ability to control direct access, because the device driver is the guy who understands the device, and he's the guy who can make the decision whether one application can have access to it, whether multiple applications can have access to it, and so forth. We needed multitasking in this operating system, but we also didn't want to have a performance degradation from DOS 3. That's one of the things the users really understand. They can run DOS 3 under 286 boxes. They can run DOS 3 under 386 boxes. They see performance degradation from multitasking. They're not going to be very happy about that. And we could argue as professionals that it's worth it because look at all these benefits you'll get running these other applications. But the users won't see those benefits right away. What they'll see right away is the performance hit. And then furthermore, even if the users didn't complain about the performance hit, our goal is to provide the maximum response to the system. And DOS 3 is the maximum response you can provide for an application that isn't invoking the operating system, at least, because then there's no overhead whatsoever. So it was important to us that we provide multitasking, and yet we not actually show any performance degradation from DOS 3. That's the genesis of the scheduler whose orientation is towards response rather than system throughput as a whole. Okay. We wanted to produce fully customized environments for each program in that we wanted the parent to be able to control the handles for a process, to be able to adjust the priority of a process is doing work for them. We in general want parent processes to be able to run child processes in the parent's particular environment. But we also wanted to provide a standard environment for all applications that was independent of what else was running inside the operating system. These two goals are somewhat contradictory. They can be worked together correctly if you're careful. This is covered pretty heavily in the OS2 tasking model and the OS2 process model, and explains why we allow you to do some things, not to do other things, and so on. We wanted to provide protect mode environment for applications. It's very, very important in a multitasking environment that the system be stable. The advantage of a real mode DOS 3 environment is that applications can do whatever they want. It's very, very convenient. The disadvantage is that applications can do whatever they want. It's very, very dangerous. So OS2 had to provide a protect mode environment. We had to provide a stable environment so a wide variety of applications can be running. And some of those applications can be flaky and yet not damage the stability of the system. On the other hand, we wanted to make sure that anything that programs could do in DOS 3 environment that users have gotten used to doing and like doing, that those programs can continue, other programs can continue to do those things in a protect mode environment. That's the genesis of things like monitors and so on, so that people, and the application pop-up facility, so that programs, for example, like Sidekick, that people have become used to, can continue to provide similar services in a protect mode environment. Okay. There's a catch-22 involved in operating system design, and that's compatibility. Basically, you can invent a brand new operating system that's incompatible with the existing operating system, say DOS 3, and maybe you've done a brilliant job of inventing this operating system, but it's incompatible. It doesn't run DOS 3 applications. So you'll take that down in a computer store and try to start selling it to people. And they'll say, this is a wonderful operating system. Which applications run under it? And you'll say, well, none yet, but pretty soon. And the users will say, well, gee, I'd be happy to buy your operating system. As soon as you got the soft sell 10 most popular applications, then I'll buy your operating system from you. So then you get on a plane and you fly out and you see the major ISVs and you show them your new operating system and tell them how wonderful it is. And they're really impressed and they say they love your operating system, and by the way, how many copies have you sold? And you say, well, actually I sold 2, one to my mother and 1 to my brother. And they'll say, well, that's great. When you sold 2 or 3 million copies, and come back to us and we'll be happy to convert our applications onto this operating system. That's basically the catch-22. The operating system won't be popular without application support. If you don't have application support, the operating system won't sell, yet you can't get application support until the operating system does sell. So basically the way around this is provide upward compatibility. You want to provide some facilities in the operating system so that people will want to buy it right away, even when it only runs primarily old applications that the user already owns. Then at that point, you can sell enough copies out into the field to interest ISVs to produce new software. That catch-22 is a key issue why we have the real mode compatibility box, what we call the 3X box in this product. A tremendous degree of effort was necessary to support the 3X box. Literally years of development went into it, many man-years worth of effort. Gave the developers a tremendous amount of grief, but the reason we did it is that we just couldn't live without it. It's this catch-22. So that's why there's the degree of support for real mode applications there is in this product. Real mode versus protect mode. Let's talk some about some of the constraints of the system that we had. It was important to support real mode, I just discussed that, but real mode is incompatible with protect mode. This caused us a major problem. The processor, the 286 processor, was designed by Intel to run in one mode or the other, but not to switch back and forth. You can switch, you boot up in real mode and you can switch to protect mode, but there's no way to switch back again. This causes a great deal of consternation at the beginning of this project. We eventually developed a technique that we call mode switching, where we do switch back again. We basically switch back again by master clearing the processor right in the middle of running its multitasking operating system. The processor then goes, this is on the hardware sense, you assert the master clear line. The processor forgets everything, loses everything, goes up to the boot sequence, partway through the boot sequence, a flag is discovered saying we're not really booting the system up, we're actually just switching back to real mode. The processor then jumps into some special code. We try to pick up our lives where we left them off earlier, and we're back alive and well in real mode. This technique was actually not completely unknown at the time that we began work on OS2. The IBM AT ROMs, for example, had some support in this. It was used at boot up time to deal with issues like diagnosing high memory and so on. The key thing is that the code in those ROMs and the mode switch code was used primarily at boot up time for diagnosis, and it was also used occasionally for accessing high memory at runtime in a single tasking system where nothing else was taking place, just the CPU was running. What Microsoft wanted to do with OS2 was to have mode switching work in the middle of a multitasking operating system. DMA is taking place, interrupts are taking place, work is going on, interrupts are queuing up, and in the middle of all of that, we're going to master clear the processor to switch modes. When we first proposed this idea, it was met with some degree of skepticism, but suffice it to say that the idea was proven to be workable, and it works today. Okay, another major constraint we had was running applications in real mode. I discussed the need of running applications in real mode, the catch-22 if you can't run applications in real mode. But there were great many problems that came up to deal with that, and you can see some evidence of this problem in a few aspects of system architecture. Some of these problems aren't obvious at all. You might first just look at the DOS 3 manual, say, heck, I can emulate all this stuff, there's no problem. But a variety of entertaining issues come up. For example, file locking. This is a multi-program environment, so you may have multiple processes that are trying to use the same file. If they try to write the same file, or one person tries to read it while another one writes it, the system's going to fail. So OS2 contains a file locking mechanism so that applications can refuse other applications access to a file that's in use. The problem is, if you have a real mode application who tries to read one of those files, what's going to happen? You can't give them an error code that says you were refused because some other process is using it. There is no such error code, and there is no DOS 3 application that would recognize such an error code because there couldn't be some other process. So real mode programs are written not to be able to understand this situation. We eventually had to route that through a hard error mechanism to make that work correctly that involves user intervention. First, we do some retries and some pausing and so on. We make a variety of decisions based upon the various modes of the people using the file. And eventually we can bring it to the attention of the user that we'll have to fail this application. We explain to the user why it's being failed. There's a thing called network piggybacking that came as a surprise to us when we followed it through initially. Basically, there's a mechanism by which applications running in memory can use int2a, I believe it is, and int5c, the networking interrupts, to talk over a previously established virtual circuit. At the far end of the virtual circuit on a server machine, you can have a special private server running that looks at the packets that are delivered to the network server, and when he recognizes a packet that's his own special format, the parasite server can basically hook that packet out and respond to it. So a variety of people wrote packages that use this mechanism. They piggyback the virtual circuit to the server box to have an interface between an application running on a client box with another special application running in the server. Well, one of the things that this protocol that these piggyback guys used, and the protocols that the redirector used for the file system networking, was there's no targeting in the messages that are sent back and forth. So in other words, the redirector sends a message saying, read me this file, and the response message that he gets, the next message that comes back over the wire, must be for the redirector. He assumes that. Who else could it be for? There's no name associated with the message. When an application who's piggybacking the network sends a message up over the wire, the response that comes back, the next packet that comes back must be for him. And he understands that because there's no one else that could be receiving that message. In a DOS 3 environment, it worked out well. If the CPU was running the application could issue piggyback messages, but there was never any confusion because the application wasn't calling the DOS at that time. If the application did call the DOS and therefore invoked the redirector, there couldn't be any confusion because the CPU was inside the DOS, the CPU couldn't be inside the application, so if the redirector is running, the piggyback couldn't be. If the piggyback was running, the redirector couldn't be running. And they were mutually excluded by fallout from the single tasking architecture. In a multitasking OS2 environment, that doesn't work anymore. You can easily have a piggyback guy send out a request and the redirector send out a request right after each other. Then a reply comes back. Who is the reply for? You just can't tell. Major problem. So you end up with a bunch of interlocking code. What happens if an application who's piggybacking the redirector, the network, sends out a message and says, I want interrupt time asynchronous response at this address. Then the application dies. Well, we can't free up his memory and give it to somebody else or give it to the next real mode application because there's this network request that's going to be responded to in a little while and it's going to damage memory. It's going to write this response right down there in memory. Well, what if the network request doesn't come back? How long do we wait for it? What do we do if it doesn't come back? Is there some way we can clear the request? Is there some way we can intercept the response coming back and short circuit it before it damages the successor program who wasn't involved in its request? A great deal of very complicated issues came up. And I already mentioned we had popular function compatibility issues. Some of the things that popular programs do today, they hook a lot of vectors, they do a lot of quick and dirty things inside the operating system. Architecturally, those programs are very, very dirty, but in terms of user acceptance, they're also very, very popular. We had to understand what those applications did. If it was a popular application, it didn't matter whether it violated the rules, it didn't matter whether it poked the DOS, it didn't matter whether it did things that we'd said you should never, ever, ever do. If a program did it and the program was popular, then that thing was not a sin. The thing that the program was doing was virtue, and a virtue we were forced to support. A great deal of effort went into that. Okay. Another issue that we had to deal with was family API. This is also related to the catch-22 of development. I'll come up to an ISV, for example, and say we've got this great new operating system and it's starting to sell and 10% of the machines are running this new operating system. The ISV is pretty reluctant to write his application so that it only runs into that operating system because he's locking himself out of 90% of the market. So it could turn out that this ISV has got an idea for an application that only runs under OS2. The application can't run successfully under DOS 3. And because he thinks it's such a great idea that people will still flock to buy it, then that guy will actually write his application to run strictly under OS2. But in the case where an application doesn't have to run under OS2, it could run under OS2, it could run under DOS 3, why would people ever want to write an application to run in the OS2 environment when they could write it for the DOS 3 environment and run it in the real mode box? For that reason, we developed a mechanism called Family API that allows you to create a program that will run in protect mode in an OS2 environment. It will also run in real mode in the DOS 2, DOS 3 environment, the same exe file, the same binary. This allows people to produce applications that take advantage of the OS2 environment while still not breaking compatibility with the large number of machines that won't be running OS2. As more and more machines begin to run OS2, then eventually people will lose interest in that and stop writing them to the Family API. But initially, Family API will be very important for the acceptance of the product. Okay, another issue of compatibility that may not be immediately obvious when you think about it is network client compatibility. We talk about upward compatibility in operating systems. Future releases of the operating system has to be to run earlier versions of the code. But we never actually talk about backward compatibility where earlier versions of the operating system have to run future versions of the code. That'd be very, very difficult to do. But you do have that problem in the network environment. If I have version 2 of network software out there, you can bet that somewhere over that wire there's a version 1, and also somewhere over that wire there's version 3. So all versions of the networking software have to talk with some degree of success to all other versions of the networking software. That's another major design constraint that had to be dealt with. Okay, let's talk a bit about design religion. We had at this point, we had a list of things that we had to do, we had a list of things that we had not to do. A variety of restraints were placed upon the system. There were still some decisions that the system designers were allowed to make. There were still some things that weren't completely nailed down yet. And what basis do we use to make those decisions? We basically make them on the basis of what we call design religion. Religion being a series of guidelines that you use to try to determine which way you can make the decision. What characteristics of a decision would be good? What characteristics of decisions do you consider to be bad? It's important to have a good religion. It's also important to have a consistent religion. If you have one group of people who think that speed is more important than space, so they're wasting space for high speed, and another set of people who are working on the same project believe the opposite, then what you'll end up with is a product that meets neither of those goals. And it isn't very successful at all. So it's important that the religion be correct. It's also important the religion be consistent. You're better off with a religion that's 95% of perfect, that is followed correctly, than you are a religion that's 100% perfect, it's only half the time followed. The key religious elements that we had in the design of the system, the first one and the most important one is maximum flexibility. We talk about how this is a 10-year platform. How over the next 10 years we think that this will be the primary software platform for office automation software. Well, 10 years is a tremendously long time. It's impossible to predict the future very precisely at all in this business for even 1 or 2 years, let alone for 10 years. For example, less than 10 years ago, I was working with a company that was designing an 8-bit processor. It was an 8080 processor. It was one of the very early 8080 machines. They were in a situation where they could save 10 cents by dropping the 2 high order bits off the address bus. They're talking a 14-bit address bus. Well, the idea was kicked around and it seemed eminently reasonable. Memory cards in those days were 256-byte memory cards. They were talking about a new advanced card that was coming out that was going to have 1,024 bytes on it, an amazingly dense card. So it seemed like impossible that anyone could ever buy more than 16,000 bytes worth of memory. And here's a good opportunity to save a dime in the production of this box. Well, it turns out that just for the whim of it, more than almost anything else, they decided to go with the 16-bit bus, and that worked out well. A more common example, maybe those people 10 years ago were exceptionally stupid, but a lot less than 10 years ago in the design of the IBM PC. Why is the video memory set up at 640K so they can only have 640K worth of RAM? Well, number one, the architecture limits us to 1 megabyte, so we were going to have a limit anyhow. And as for why 640 was thought to be okay, well, 640 was 10 times more than the very largest machines that existed in those times. In those days, 8080s were the dominant machine, and 32K was a common configuration. Rich people had 64K, 10 times over the size of what rich fat cats ran. That seemed like an amazing amount of memory. That decision was made without much hesitation, and yet today's 640K is considered to be laughingly small. It's almost impossible for us to envision what the future will look like. So the way we tried to support the future is by providing maximum flexibility. We want to arrange for functions and techniques that allow the system to be expanded in arbitrary directions. We also wanted to make sure that everything that we offered today could be supported by compatibility in the future operating systems. I explained how we spent an incredible amount of our time dealing with characteristics and issues so that we could support DOS3 programs. Those DOS3 programs got their crazy ways because of DOS2. And DOS2 got its crazy ways from DOS1. And DOS1 got its crazy ways from CP/M. And as you can see, it goes back. So we wanted to take advantage of this opportunity when we're basically starting with a blank sheet to make sure that we didn't design any characteristics that we'd regret in the future. And we come up with OS 42 5 years from now. We want to make sure that OS 42 can deal with OS 2 kind of programs in an easy fashion, that we won't have done a bunch of things. I won't be standing in front of you 5 years from now complaining about how much trouble it was to support OS 2 programs. So all the OS 2 functions that you see, each one of those functions has been designed in such a fashion where it's sufficiently abstract and sufficiently generic that whatever kind of operating system we might envision, that we can at least support these things. It may turn out these new operating systems are so different from what we have today that nobody's interested in doing it in these silly archaic manners. But so long as there's any interest in doing it in these fashions, we know for sure that we can support that. Another key characteristic of our religion is stable environment. We'll be running a lot of different applications in the system. Those applications will come from different vendors. There's sure to be mistakes happen inside the software, mistakes from the users for that matter. We've got to make sure that the system remains stable. Even today, running DOS3 on my home machine, I have a couple of terminate state resident guides. I run a variety of applications in different order. Every couple of days, the system crashes out. I don't know why it crashes out. It's hard for me. I haven't been able to determine what the pattern of events it is that's causing this crash. I haven't wanted to take time to borrow an ice from work and debug the thing. I could spend a man week on the thing and actually solve the problem. But that's not the point. The point is that here I am, a DOS3 expert, and when the system's unstable, I'm sort of helpless. Imagine what the end users are like. The office people, when their system acts strange, there's just nothing they can do. For the system to get the kind of acceptance that we all want it to have, it has to be extremely stable. When a program does something wrong or there's some error comes up, that error needs to be isolated as much as possible to that program. When a program does something wrong, it should damage the system and other applications to the absolute minimum degree. We don't rely upon programs doing the correct thing. We keep track of all resources, for example. And if a program fails to return resources before it terminates, we'll return it for them. We make sure that nobody can orphan components of the operating system. We never ever trust an application to do the right thing. An application should do the right thing. If it fails to do the right thing, then the OS can't do the right thing for it. That's the whole thing problem, to understand what the application should have done. But the OS makes sure that even though the application itself may have failed to do what it's supposed to do, it won't interfere with other people doing what they need to do, other applications. Also, another characteristic of stable environment, when something goes wrong, it's important that the indication that something went wrong be kept as close as possible to the source of the failure. In other words, we don't want to say, one of your applications is bad, we're going to halt the system. The user will never be able to figure out what's wrong. We want to make sure that when an error takes place, that the user can figure out which application caused the error. So at the very least, the user can just stop running that application. Finally, the software tools approach. This is the approach that was discussed a little bit earlier in my talk, where I talked about the necessity of applications doing everything themselves. We think it's important in this environment where facilities become much more powerful. We have a lot of memory, we have a lot of CPU resources. It's very, very important that there be modular and standardized interfaces between applications so that applications can make use of other standard system services. Presentation manager is a system service that should be used very heavily. The network is a system service that's used very heavily. The operating system itself is a system service that's used very heavily. Other services will be developed, arbitrary services that will come into the dynamic link interface, and we need to make sure that our architecture supports that in a very, very flexible fashion. Something about the future. One of the things we'll have in the future clearly is a new file system. We'll get away from all the size limitations, we'll get away from all the fragmentation limitations of the fat file system. We'll definitely get higher efficiency file systems. Current file system is actually reasonably effective, except in a floppy environment. We'll make it more effective than that. We'll reduce the degree of fragmentation on the disk while maintaining a high degree of locality for efficient disk access. We'll go into unlimited size, as I mentioned. We'll also have provisions for worm disks and ROM disks and so on, CD-ROMs and disks of that nature. That includes provisions for disks whose performance characteristics are considerably different than the perfect DASD device. The perfect random access device is random access, equal time to get to each piece of data. That's not true for disks, although it's mostly true. It doesn't take a whole lot longer to get to the worst case piece of data as it does to the best case piece of data. But there's still a considerable difference there. For some disks, for example, CD-ROMs, the difference between the nearest data and the furthest data can be very, very large. If it's a read-only device, then there may be nothing you can do about it. If it's a read-write device, such as a laser worm device, then you may want to modify your file system very considerably to support that. Future versions of DOS will have support for such file systems in it. A fully protected environment. I made reference to this earlier. In the 386 platform, we have a virtual real mode box so that we can run real mode programs unchanged and yet be fully secure against them doing anything nasty. We also have an I/O bitmap mechanism that's in the 386 that will allow us to provide selective I/O access. So we can say this application, it's okay for him to write to the screen controller, but it's not okay for him to write to the disk controller. For people that have 286-based machines and want to go to a protect mode environment, it won't be that expensive to upgrade to a 386 from an architectural standpoint. People are producing drop-in 386 cards. They're rumored to be drop-in 386 chips and so on. Those things will come about and they'll be comparatively inexpensive. So somebody who has a 286-based machine and is happy with the 286-based machine in terms of its performance and its size and so on, but wants a fully protected environment, he can always upgrade to that by just swapping his processors to a 386. Finally, enhanced network support. I won't discuss enhanced network support very much. There'll be some discussion of it from Daryl Rubin in the networking group. All I can really say about it in the scope of my talk is that networking is a key feature in the office automation environment, and Microsoft intends to support it very vigorously.
For additional information on the topic we just covered, be sure to take a look at the written questions and answers that accompanied this videotape.